Okay, welcome back everyone. In this video we're going to talk about how to analyze motion graphs using areas. And so what I've done is taken one of the examples from the slopes and areas worksheet, and we're going to come down all the way to acceleration. And remember that one of the goals of this unit is to try to unify our description of motion using graphs and equations. And if you just look at this graph down here, it doesn't seem very exciting. It looks like we could describe it as A equals a constant. And that's fine. But remember that we can also analyze this a little bit differently. If I look at the area of this graph, what am I doing? Well, I'm multiplying acceleration and time. I can use unit analysis to see that meters per second squared times seconds is going to get me something which is in meters per second. So the conclusion to draw is that the area under an acceleration versus time graph is the change in velocity. Now I say change in velocity because we start at one value and go to another. It's not necessarily the final velocity, it's the change in velocity. Now to just keep things simpler, we're going to pretend like V initial is 0. Okay, so that means that if I calculate the area under the graph will give me the change in velocity. So here's how it works. Alright, so let's just mark this off. Whoops, let's fix that real quick. And let's mark this off. And let's just call this 1, 2, and let's do something kind of silly. You'll probably see why in a moment, but let's go 4, 8, 12, 16, and so forth. Okay, and of course this will be 1 second, 2 seconds, and so on. So 1, 2, 3. The units don't matter too much for acceleration. This is just to show you the behavior. So first of all, let's look at the area contained in this rectangle going from 0 to 1 seconds, and it looks like this is an area of 2. Okay, so 2 is going to be the value of the velocity. That is how much our velocity has changed in the first second of travel, because we've taken acceleration and multiplied by time. Okay, so that's 2 right there. Now let's do it again for the next one. And guess what? That's another 2. So now instead of being at a velocity of 2, we're going to mark it at 4, because the total area starting from 0 going to 2 is 4. So on and so forth. This is also 2, this is also 2, and you get the idea. So every time this is going to go up by 2. Whoops, wrong place. How about right there? And so when I draw in a trend, that's my velocity. Now this should start to look familiar to you. As a matter of fact, the equation for this line is V final equals V initial plus acceleration times time. Okay? And guess how we get back to the acceleration? Well, to find the acceleration we take the slope, and y equals mx plus b. So go back and look at the more about slopes video for more information on this. Okay, so now let's take this one step further. Now that I have my velocity graph. Oh, and by the way, do you notice that in my graph here I have v initial is equal to 0? Okay. So now let's take it one step further and let's write this. The area under a velocity versus time graph is, okay, I'm going to let you take a guess. Pause it and take your best guess. Alright, did you guess? Well, if you couldn't figure it out, again, unit analysis comes to the rescue. Meters per second for velocity, seconds for time is going to give us meters, which is the unit of displacement. So the area under the velocity versus time graph is displacement. I should probably rewrite that as the, so you don't think acceleration. How does this play out? Well, we do the same thing, and the area calculation is very similar. Okay, here we have a triangle at 1 second. All right, that let's see here. It's got a height of 2 and a base of 1, and it's a triangle. So we're talking about an area of 1/2 times base times height. 1 times 2 times a half gives us a value of 1. Okay, so I'm going to put that, let's call this 2, let's call this 4, 6, 8, and I'll actually call this 10 and 12. You'll see why in a minute. So 1 is right there on my x graph. Notice how I'm doing exactly the same thing. I'm finding the area of the velocity graph and putting the value on the position graph. Likewise, let's take the next chunk. Uh-oh, that's a trapezoid, but it's an easy one to figure out. I draw a line straight across, and this is a rectangle of area 2 and a triangle of area 1. That's a total of 3 more. So we add that to the 1 that we started with. 1 plus 3 is 4. Okay, and we keep going. Let's look at the next one. Oh, well, this is a square of area 4 and a triangle of area 1. So that's 5 more. What's 4 plus 9? You guessed it. This next one is going to be at 9. Okay, and so on and so forth. This is a square of 4, a rectangle of 2, and a triangle of 1. A square of 4, a square of 4, triangle of 1. You get the idea. Notice what's happening? This position graph is not increasing at a linear rate. It's actually increasing at a quadratic rate. Because let's look at what our areas are. Okay, so our areas are 1, 3, 5, 7, 9, so on and so forth. Okay, so the total distance is going to be those added up, and this next one is way up here at 16. As a matter of fact, we connect those dots and pretend like I can draw, and if I can draw, we get a nice parabola. Why do we get that? Because position final is equal to position initial plus v initial times time plus 1/2 at squared. And we'll talk more about this equation a bit later on. But even if we get rid of x initial and v initial because that was 0, we still have a parabola. Okay? And the important thing to see is this. The acceleration graph is something along the form of a equals t to the 0 power. What's t to the 0 power? Well, that's 1, and then we have a constant. This one, the velocity graph, is something like v equals t to the first power. And where's that 1? Well, it's right there. See the pattern? The next one is position x is something t to the second power. And there it is. So this is very interesting that this actually tells us a lot about what's going on. And if there are any calculus people out there, you will recognize what it means to take the area under a graph. We're talking about the I word. We're talking about the integral. And I'm just applying simple power rule for those of you who are familiar. But the important thing is that now we have a way to link graphs together using areas as well as slopes.